Hi, we're going to start a new unit today, acids and bases, as the title shows. We're just going to dive right in. Hope you have your notebook ready, your pencil ready, and let's get started. So as a quick do now to get you thinking about some content that we talked about several months ago, I want you to read this and make your guesses, your assessments based on your prior knowledge for these three substances based on what you know. You feel free to pause the video if you got to go back and look at something, or you want to check the answers online, I guess. You shouldn't do that, but anyway, you can hit the pause button and think. Right, so hopefully you took a second for that one. And as you probably have guessed, first off, let me switch my color. This one is going to be electrically conductive, salt water, of course. You remember the story about the hair dryers and the GFCIs. Sugar water does not conduct, and then based on that pattern, you might assume that the HCl solution would also not conduct. That would be my answers. We're going to go with it, but of course, that wouldn't really be a lesson if that actually took place. So really quickly, I'm going to play this video where they actually test the electrical conductivity of hydrochloric acid solution. Oh, that kind of ruins it, doesn't it? Well, watch anyway.
Electrical conductivity for HCl and water. Here we have a light bulb. I'm just going to show you that it's working. Now I'm going to dip these two electrodes in water to check if water conducts electricity or not. As you can see, there is no light. Now I'm going to add some of concentrated HCl, hydrochloric acid. And I'm going to check again if it conducts electricity or not. As you can see, the bulb is on.
Right, so that's new. The one thing I want to point out is that they showed that bottle was concentrated HCl. I think a lot of people will mix this up when they're thinking about it. Hydrogen chloride, the compound, is actually a gas at room temperature. So usually we're talking about, when they say HCl, we're talking about the aqueous solution. So even though it looked like it was a liquid, it's actually a solution. But anyway, this completely disagrees with any assumptions you might have made over here. And the reason for that is, well, this next unit. So just as a brief review of why we expected to see what we expected, and then why we actually saw what we actually saw will come up later. Just to compare, when sodium chloride dissolves in water, you get, of course, sodium chloride aqueous, which is found on table F, which then would dissociate into, and this aqueous. Remember that these are ionic compounds. Ionic compounds separate in water because water has an attraction for the ions, and so what we get here is mobile charges. When we're considering like sugar, and when sugar gets dissolved into water, sure, the crystals break down, but the individual molecules don't separate from each other. You don't get C's and H's floating around on their own, so nothing happens. So you get mobility. You get mobile non-charges. So this is why you're seeing conductivity here and why you're not seeing a conductivity there with the sugar water. Now this is because this is ionic and this is covalent. So if we're considering something like hydrogen chloride, which is covalent, you might assume that what you get is HCl aqueous and then you'd be done. But the problem is you get conductivity, which, I mean, based on what we're seeing with the ionic compound, we have mobile charges. So the question becomes, how do you get mobile charges when a covalent substance dissolves in water? We know that it happens, so we kind of have to like reframe our understanding of how certain covalent compounds interact with water. So, I mean, I kind of want you to take a minute here. Feel free to hit the pause button and draw out a molecule of water and draw out a molecule of HCl and see where some interactions might take place. This would be a time where I ask you to work with your neighbor. You can't work with... I mean, if you guys are watching together, just... Not together, like 6 feet. Anyway, let me just draw the structure. Right, we have our shared pair of electrons, then we've got our lone pairs. So this is our covalent molecule. Need to erase. Now, remember when we talked about sodium chloride, that was a plus, and then you got your full ionic charge here, right? So your electrons are totally separate. When your water comes over, you get your positive side of water having an interaction with the negative chloride ions, and you got the negative side of another water having an interaction with the positive side, the sodiums. And they pull the ions apart, and that's where you get your conductivity. Well, clearly something similar has to be happening here. Now, what we're doing is we have to separate our H and our Cl, but if we separate our bond evenly, what we end up with is two neutral atoms. So that can't be right. This isn't what takes place. What has to happen is these electrons, even though one was supplied by each atom to make the bond, when the water separates when it dissolves, you get separation of the atoms, but you get separation in an uneven way. And the only way this makes sense to me to think about is, well, we wrote some full charges here. We know that in an HCl bond, that the chlorine has a higher electronegativity. So that's going to be a slight negative and a slight positive. That's as a molecule. In water, what we actually see is these two electrons go fully with the chloride based on that high electronegativity, so that when HCl as a gas dissolves into water, we get H plus aqueous and Cl minus aqueous. So that this now looks the way that the ionic sodium chloride dissolves in water. So we see a similar pattern. I mean, this is neat, but the problem is we have a covalent substance that dissolves and then dissociates, splits into ions like an ionic compound, even though it's not an ionic compound. And this is my simplest definition for what an acid is. Covalent compound that creates ions when dissolved. Now, this is my definition of acids and bases, of an acid. And of course, I like my definition, but I'm not that important that I get my own name for it. The operational definition, the idea is that a definition of an acid is how an acid behaves. Our definition that we're going to use in this course it's named after a scientist named Arrhenius. It's a little bit more elegant than what I'm saying, but it kind of gets the point across. An Arrhenius acid is a substance that creates H plus ions as the only cation in solution. So I've got here table K. It's above my head. It's all of the common acids you are responsible for knowing for the regions. Now, if you look at these, I see some patterns. Again, that's that chemical intuition thing I mentioned, but hopefully you see something similar too. In most of these, the first element is an H. Here they're showing it weird. but there they're showing it in the front. This structure here, we're not going to talk about this guy too much. This is an organic chemistry thing. I want to focus on the bottom one today. This guy too. Carbonic acid, not going to focus on the CO2 aqueous. We're going to focus on the H2CO3. It kind of backs me up here. But this tells me that these substances, if they are acids, and it does name them as acids, when they dissolve into water, what you get is that HCl in water does not exist as HCl, and instead it exists as H plus and Cl minus. And something like HNO3, which, NO3 from table E, we remember is nitrate. So we get H plus and NO3 minus. And then something like, sulfuric acid. Keep in mind that, if these guys are behaving the way ionic compounds do, remember that sometimes that subscript will actually imply that there's more than one of a given ion in your compound, and when you dissolve it, you get, multiples of that. You get 2 moles of H plus for every 1 mole of sulfuric acid. Again, but this is our common thread. They all create H plus aqueous. I want to mention something here that will come up at some point. I think I might gloss over this today a little bit. I'm going to record some other videos, hopefully, and fill in the blanks as we go along. But when you have this H+, some textbooks will say this, and I do encourage you to read your textbook if you want some more explanation for this. The H+ ion in water doesn't really exist as an H+. It exists more as attached to a water, and this is what we call hydronium. So another way to word this is that an Arrhenius acid is a substance that creates hydronium ions as the only cation in solution. Simple enough definition is that when you dissolve it, you get H plus, and you don't get any other plus, or you get H3O plus, and you don't get any other plus. The reason, though, why we have this separate definition, aside from the fact that you have covalent substances that are being ionic in solution, is more in the behavior of the acids when they're in solution. You remember acids and bases in the past, probably in like a 7th grade or 5th grade. Like you've heard of the term. But we're just going to go through some general properties. Of course, the first one we've already mentioned and seen, conductive. Now, when they conduct, you've got your ions and they're mobile, but really the ion of the H plus is pretty interesting because what you'll see is that, especially in high concentrations, that this is caustic, corrosive, damaging to metals and biologicals. We've seen in labs where zinc or magnesium reacts with an acid and it slowly degrades and dissolves into the solution. If you get acid on you, it's not so great. The one little gross example, there's stomach acid. You have acid in your stomach, but if you're unfortunate position of having to throw up, that burning sensation you get in your throat is some slight tissue damage to your throat because of that acid. Of course, you probably remember that the pH is a thing. It's a way to measure the acidity of the solution, and for an acid, the pH has to be less than 7. And the last thing I'll mention, two things, sorry. The first is that turns litmus red. It's a good indication that you have an acid, and most of them are in fact sour. I mean, acetic acid is it's vinegar. It's the active component of vinegar. There's obviously some water in vinegar as well, but that's not where the taste comes from. Carbonic acid is found in soda and seltzer, and that slight tanginess you get when you taste seltzer or soda, that's, at least in terms of seltzer, it's because of carbonic acid. In soda, there's some other chemicals there. So if you were to drink some of the more dangerous chemicals shown on this list, they would be sour. They'd also be incredibly painful, so don't do that. But that's the general properties of acids. So the other side of the coin, whenever you talk about acids, you have to talk about bases. Let's take a look. Let's kind of try and go through the same process. Again, here are the common ones that you're expected to know for the regions. So let's take a look at what's the same and see if we can find a pattern. I see hydroxide. But you know what else? I see sodium, potassium, calcium. These are metals. And hydroxide's a polyatomic ion. These are ionic compounds. So bases would be ionic compounds containing hydroxide. Now, the Arrhenius definition would go a little bit more detailed, and like with the acids, an Arrhenius base is a substance that produces hydroxide as the only anion in solution. And then similar, just to see the process of how it works, sodium, oops, I'm going to eraser. Sodium hydroxide solid, when it dissolves into water, what you would see is a sodium ion, because this is an ionic compound, and you'd see hydroxide. And then, similarly, when you dissolve something like calcium hydroxide, stoichiometry being stoichiometry, you would create calcium ions. Remember, calcium's a +2 in group 2, and you get 2 hydroxides. So again, our common thread is this hydroxide ion that gets created when you dissolve. You don't need to worry about like special definitions or what it does with water. This one's actually a little bit more straightforward. These are ionic compounds, and they do what ionic compounds do. And so again, if we dissolve this into water, we should pretty much see it be conductive. In fact, if a substance dissolves in water and the solution is conductive, you can be guaranteed that one of the 3 substances that we've talked about are present. It's either an acid, a base, or a salt. That's why collectively we refer to these things as electrolytes. Electrolytes, acids, bases, salts. The 2 go hand in hand. Similarly to acids, but maybe in a different way, these are also caustic materials, and they're corrosive as well. Interestingly, I can maybe find some videos to upload. I'm making a mental note. Turns out that an aluminum can will get dissolved by acid. It'll also get dissolved by base. It's a different chemical reaction, a different process. I think I might have done that with one of my classes this year. But interestingly, it has a similar outcome, even though the chemistry, the method is different. Here what we'll see is that our pH values are greater than 7. And here we're going to see that return litmus blue instead of red. Typically blue colors will be indicative of a base or a basic solution, and reds will be indicative of an acid. Some people will say that bases taste bitter. That's not entirely true. Like at all. Many of them don't taste bitter. A lot of people say it, so I'm going to mention it. So some are bitter. There was a teacher I taught with years ago. He made a big point of this. He's like, the bases don't taste bitter. If you were to eat sodium hydroxide, you would not say it was bitter. It's a salt. It's a metal hydroxide. He's like, I've tasted it before. It doesn't taste like it. It just tastes like salty. And I'm like, okay. Don't eat soda. Don't do it. Just don't do it. I looked at him like he was crazy, and I'm sure you've seen that look out of me before. Don't do it. I've never done it. I don't want to do it. There's just not worth it. It's not worth the experiment. Anyway, sidetrack. But those are your general properties of bases. So to apply this, though, what we really need to be able to develop the skill of is looking at a substance and being able to identify it based on the chemical compound as maybe an acid or base or neither. So take a couple minutes. I want you to look at these substances, hit the pause button, write them down in your notebook, and try and identify acid, base, or none of the above. So hopefully you took a second to go look through that. Obviously the first one, nitric acid, it's on table Okay, oh my god, I forgot to mention, there's also a table for bases, right? That's table L. So you should be using table K and table L like a lot in this unit. There's several other tables we'll look at, but this one is an acid. Calcium hydroxide shown on table L, that's a base, pretty clear. So this substance, it's a little bit misleading. You might look at it and go, oh, there's an H there. Does that mean it's an acid? Well, it's not on the acid list. And like I said, if it's not on the acid list, you can be reasonably sure it's not an acid unless a given problem is telling you something additional. And I didn't tell you anything additional here. So this is neither. Now for this one, I think this is very misleading because you see an H and it's separate from the other H's, and you also see an OH. So you're like, is it an acid? Is it a base? What is it doing? Actually, in this case, this is a substance called methanol, and it's neither in terms of the region. Take post-AP chemistry down the road. We can talk about ethanol and how it works. It's neither. If it's not neutral, it's like this. It's neutral. Just call it neutral. It's not an acid and it's not a base. Interestingly enough, to look at the chemical equation. And then this one here is glucose, and I included a structure. This is a Fischer projection. We see a lot of these OHs all over the molecule, and then we also see all these H's here. And so you're like, is it an acid? Is it a base? I don't know what's going on. How many times can you say acid in a single presentation? Again, this is neither. Not all H's mean acid, and not all OH's mean base. The best rule of thumb for you is to just read the reference table. There are patterns there, and I can talk about them. It might help, but it's the safest thing is just check the table, and check the table. So just to sum things up, acids and bases are weird. New definitions, new properties. But by the Arrhenius definition, acid means H plus aqueous or H3O plus aqueous. Base means hydroxide, OH minus, aqueous. Here are your pH, it's a thing, greater than 7, pH less than 7. More properties, go back, read the properties, you should be familiar with them. But typically, the easiest way you can point one out for this course, metal hydroxides. So like sodium hydroxide, lithium hydroxide, iron hydroxide, copper hydroxide, metal and a hydroxide, that's typically your base. For acids, there really isn't a firm rule to just tell whether or not an H in a covalent compound is an acid H or a non-acid H. That's not entirely true, but we're not going to worry about it today. Here's the best thing you can do. I mean, you notice this. If you go back and read table K really quick, you notice this, especially in this compound. They separated their H's, and then typically, especially for this one, they'll put H's at the front. And I think that's, while that's definitely not an every time scenario, if you see a compound that's in the form H something, HX, H and a bunch of other stuff, a lot of times that H, that's an acidic H, and it will fall off when you put it into water and create an anion to go with it. Thanks for watching.